moving on to our second speaker, who's one of our sponsors as well, Veritas, Giles Hall. I've actually known Giles for quite a long time. Me and Giles work together in the hardware verification world. Giles is working for a company who produced an automated tool for hardware verification, which is based on constrained random test generation and functional coverage. And I know Giles is now working on an area like that in software testing. But I'll hand over to Giles.
Okay, thanks very much, Mike. Firstly, thank you, Dot. That was just was brilliant. I think it really helped me understand a lot of the way testers think and that stuff. And I'm coming here now as a tool vendor, trying to sell an automation product, and I'm feeling a bit, actually, am I doing the right thing? No, but actually, I think one thing I took away from Dot's presentation, which I think is really important, that it's not automation that finds bugs, it's tests that finds bugs. And the area of automation that we're working in is trying to automate the generation of the tests. So actually using a randomized approach to help you generate vastly more tests. And that's really what I want to talk about today. So I think that actually fits really well with the sort of things that Dot was talking about. Just actually automating the running of the test doesn't necessarily find bugs. But automating the generation of tests and what you're actually testing and expanding that is a whole different game. I think that's what I'd like to talk about during this. So I sort of want to start from the sort of premise, I guess, that we're all here, we're software testers or we're software developers, and we're all developing software for our various customers. And the problem I think that we all face is that the state space or the path space inside our software is vast. I mean, and we all know, even when we've written a very small piece of software, just the amount of testing that we need to do to fully test it is just enormous, and we just can't imagine how we're going to do that amount of testing. And so the best practice probably for more than a decade or so has been to say, okay, well, let's sit down with interested parties, maybe even marketing people in the room, and let's understand how the customers are going to use our software. Let's develop those into use cases, and then let's code up each use case into a test case that they're then going to run, check that the design actually does what we expected it to do. There are many problems with this approach, and I guess we all know it. I'm sort of preaching to the converted, I'm sure, in many cases. Firstly, of course, it's a manual approach. We have to sit down, and it's only the things that we think of in that room with all those people that we actually code up and turn into test cases. And so that's a big problem for us. What about all the things that we didn't think of? Those are significant issues. Of course, it's a manual process, so we have to take those use cases and turn them into test cases, and that manual process is flawed and has problems with it as well. And of course, the problems that Dot talked about, once we've built that test case, we've invested all that time and effort thinking up the scenario, coding up the scenario. We may have spent hours, days even, of effort for each use case. We then run it in maybe minutes, and then its job is done, pretty much. If it finds bugs, then that's fabulous. If it didn't find bugs, then all we can really do with it is put it into our regression suite, keep on running it, and exactly as Dot was saying, that's not going to find new bugs. That may tell you that you've broken it in the future, you've done something bad that's broken that software, but it won't find fresh bugs. So really we have to start to think about how we do more use cases, and that's really where we started Veritas, and trying to think about the process for automating the generation of use cases. And that sounds like it's got to be wrong, really, because that's necessarily a process where you have to involve people. A computer can't think of test cases. And that's true. And also we can do automation, and that's really what I want to talk about today. Now, there are a lot of automated tools out there. I think Dot talked about automated test running tools. Obviously, they're very popular. We use them internally. They're very important. They're very good, and we get benefits from them. There's lots of automated tools in the test world as well, static analysis type tools that tell us about code problems, about memory leaks and all that good stuff. Absolutely, we should do all of that. Those are bugs that I cause as a software engineer writing software, and I love that these tools find that stuff for me and tell me about them. But really we need to, what I want to concentrate more on is functional verification, functionally testing that what the software does, what it's supposed to do. So with this huge state space, what we really know in our hearts is that the vast majority of that state space is untouched by our tests. There are many paths, many timing differences, many different scenarios that our tests never hit. And of course, in the old adage of if you didn't test it, it doesn't work, of course, the likelihood is that a lot of our critical bugs that our customers find lie in those areas that we didn't test. So what do we do? So to improve the software quality, and I'm really passionate about making sure that we get better quality software and our industry of software developers are not looked on as poorly as we are today, to get better quality, more robust software, we have to push out into that unexplored space. We have to generate not twice as many tests, not 10 times as many tests, but thousands, millions of times more tests than we run today. And that has to be a partially automated process. It's partially an intellectual process, as test writing is today, but it's partially also an automated process. So as Coveritas, we've formed about 4 years ago now, and our aim was to really try and automate some of that test generation process. And of course, the first thing that came to mind, primarily from our history, was some form of randomization is a great way to do some automation in the test generation process. So what I wanted to do was just run through some of the things that many of us have done in terms of randomization. So first of all, of course, whatever language we happen to be using, it has built-in, it has some built-in randomization capabilities. So we could potentially say, yeah, let's just use those. Let's randomize some inputs to our functions, and I can use the rand function that's in my language to do that. Of course, if you've ever tried this, what you very quickly find is that mostly what that generates is rubbish, because there are a whole bunch of rules associated with your piece of software that that rand function doesn't know how to obey. So there are relationships between inputs. You know, the thing A must be greater than B. A value must be within a particular range. Or under certain conditions, if A is equal to B, then this new rule must apply. And when I think about the parameters being passed into my functions, there are loads of these rules. And actually what I need is a mechanism for generating that random data, but that obeys those rules. So in the hardware world, this was done with a concept called constrained random generation, and that's something that I was involved in from 2000 onwards. And the idea here was that we generate random stimulus, but it obeys a set of rules. And each time we call a function or generate data structures, we can generate that data structure obeying that set of rules. Now, naively, I guess, when I started applying this to software, I thought, yeah, that'll do. I can do that and apply it to a software tool chain, and I should be fine. We should be good to go with software engineers. I think I learned probably more slowly than I ought to have done that that wasn't enough. We needed to do more to test software because software is different. And the primary area where software is different is its history. All the software we write is inherently sequential. It has a very deep history. And what I find that I'm doing is solving these types of rules. I not only want to solve rules that say, relate these two parameters together, but I want to say, well, the previous time we did this, that has an impact on the current parameters. And because software is deeply historical, it's not just the previous time, but it's the previous, and the previous back 1,000 or whatever it is. So the state of the system and the things that I've done in the past have a massive impact on what I'm allowed to do now. So this type of approach doesn't even work for software verification. I can't take this methodology and apply it directly to software verification. And this is really where in the early days of Coveritas we hit the brick wall and said, crikey, we need to go away and rethink this process. And we came up with a way of, and I don't have enough time in my 20 minutes today to really go into the details, but come and talk to us on our stand and I'll tell you more about it. But we came up with a way with looking at scenarios through history and being able to define rules, historical rules, that say how you're allowed to execute functions or data into your system. So now the intellectual process, rather than writing a directed test that says do A, then B, and expect C, it's a matter of writing down the rules about what's the hierarchy, how am I allowed to do things, what's the order in which I can do things on my test interface, what's the rules based on test state about what I'm allowed to do next. And once I've defined all those rules, then I can start to use automation. So still, absolutely, there is a process where test engineers, verification engineers, whatever you want to call them, are involved, and they're defining the rules, defining the process by which we're allowed to talk to our system. Now, that's actually quite hard work. It's very stimulating and very interesting, and I quite enjoy doing it. Writing tests is often less stimulating and interesting. Okay. So this is really where we started, and we wanted to build that capability to solve those rules across time so that we can generate automated data into your system. So what are the other problems? So that's number one on the list, I guess, being able to solve those rules. Well, if we want to make this work for software, there are a number of other problems we need to solve as well. First of all, real-time performance. Now, in the tools that existed before, they were working in a simulation environment. Performance wasn't a big deal. Most software verification today, or certainly my experience, is done with the real system. It's done with FPGAs or with real silicon, with real software compiled onto it, and that's where we do a lot of our verification. So this system that I'm talking about has got to be able to constrain or controlled randomly generate data and pass it into that system in real time and be able to monitor data in real time and work with that. So that's an issue that we need to be able to deal with in this sort of system. Of course, we also have to be able to connect to the software that we're testing. That software might be inside an Android phone. It might be inside a controller that's eventually going to go into your car in a system. So we need that mechanism to be able to talk to it. So we need to have an open API at the back end of our generation tool that allows us to go and gain access into all of the software that we're trying to test. And it has to be adaptable so that it doesn't matter if we're working with real hardware or we're working with models. We can use the same testing methodology with both. And the last thing I just want to mention briefly is this process of quantifying. One of the biggest objections to any form of random testing is, what the hell did I do? If you did random, actually knowing what you did is critical. And I have a big test plan with thousands of elements in it that says all the things I know I must do. If I just do random and I have no idea what I did, then I have to go back and do manual testing to do that stuff. So what we need is a mechanism of being able to quantify what actually ran during our random testing, so we can say that we actually hit those scenarios. We saw those scenarios, those use cases actually being executed during test running. Now, in the hardware world, that was part of the environment. But again, from the software perspective, we need to be able to deal with this from a sequence view as well. So here I'm just going to very briefly show you. We're looking for events that occur inside our system. We're looking for chains of events that actually go to make up a use case scenario. And those chains of events can obviously contain repetitions and gaps and all sorts of things in them. So what we're doing now, rather than taking a use case and writing a test, we're taking a use case and writing a coverage model for it. And that coverage model will tell us when our random tests actually hit that scenario, and maybe it didn't hit that scenario. And then this data can all go into a database. Databases are good at this stuff, and we stick it into an SQL database, which can then be mined for all sorts of great information about what you've done, what you haven't done, what you used to do but you no longer do, all those good things. So what do we get out of this? Well, our product's called Vitaq, so you've probably seen that a couple of times now. So the main benefit that we get from this is orders of magnitude more scenarios, and many orders of magnitude. I leave our tools running continually, actually testing our tools. It sounds a bit incestuous, but we use our tools to test our tools. And they just run with different seeds all the time in the background, giving us the potential to find new bugs. It's not like regression testing. I've always got the opportunity to find new bugs because I'm running with new seeds. But when it comes to debug, of course, you need to be able to repeat that test so that you can go and debug what you did. If it failed, I need to know why it failed. And of course, our tools guarantee that if you run the same test with the same seed, you get exactly the same sequences, the same values, and all that sort of good stuff. And it actually provides some comprehensive capabilities to allow you to vary seeds in different parts of the environment. But I don't think I have time to go into too much detail there. The whole abstraction thing is good too. So we're actually now taking the testing concept and we're abstracting it up to the tester's view of the world. And again, this was something I thought that was great that came out of Dot's discussion. Am I down to 5? Okay. Absolutely, the tester wants to talk at his level of abstraction. He wants to, if he's testing a mobile phone, he wants to talk about making a call and ending a call and those sort of things. And with this approach, we can abstract up to that level and break sequences down into hierarchies of sequences to the lower level stuff that's actually being executed on the design. Let's go through some of this. Some of the other things that were important from our execution, no instrumentation. We don't need to modify your code. We can talk directly through the APIs that are there now. The really key thing here to take away is that, the methodology never ceases to amaze me that it finds bugs that aren't found in other ways. Our customers take their software and their systems through compliance test houses. They do all of that stuff. They come back, they run our types of environments on it. They still find bugs. And I think that's something that managers get confused about. Well, if my software got through a compliance test house, how could you possibly still find more bugs? But of course, the software engineers, we know. We understand why that's the case, because it's got nothing to do with compliance testing. The bugs are in there, and they're in horrible corner cases to do with timing and sequences and things, which the compliance tests just don't hit. So that's the key. These are exactly the sorts of bugs that this methodology finds. We'll quickly flip through this. So as I said, we've been going 4 years. The methodology we've been developing sort of goes back more than that, 15 years or so. But you can look at that on the website, in your books. So just to summarize then, so current practices just don't test enough of the state space. And I hope that's not too controversial. Most of us would probably agree that all the manual tests that we write just don't go deeply enough. They don't hit enough different paths. They don't do enough different timing. And they just don't go there. Randomization is extremely powerful. It's been used in many guises for a lot of time. But what we really need is control over that randomization process. And that's really key. If we have the right levels of control, we can really start to automate a vast amount of the test generation itself. I'm not suggesting the human comes out of the process entirely. In fact, most of our customers still have as many test developers as they did before. They're just working on that rule set. They're working on pushing the automated test in a particular direction to hit particular corner cases, rather than each individual use case. So the same people are being used, but they're just doing different stuff. Absolutely, coverage is key. So we call it coverage. But don't get it confused with code coverage and branch coverage and all that stuff. Absolutely good to do, but this is not what we're talking about here. Coverage in this is about test plan coverage. Have I hit those use case scenarios that I know I needed to hit in order to test my software? That's really what we're about here. And combine these two things together, randomization, the automated generation of test cases, use cases, combine that with a functional coverage methodology which allows you to see which use cases you actually hit in your system, and you have a very powerful verification methodology. Okay.
We do have time for 1 or 2 questions, if there are any questions from the audience. Oh, hang on. Yes. So, you should have learned this by then.
Yeah, it's true. That's the key to me when you said through all that was the fact that you can go back and debug it. Because, absolutely. For me, I can do loads of stress tests and find loads of bugs, but tracking it is. But surely, how long does that take to set up? Because I think there must be a massive amount of complexity in setting up all the use cases, and your tool understanding the code enough to go through all state machines.
It's a really good question, and I think there is. I'm not going to pull the wool over your eyes. There's work you have to do up front to define the rule set and to define the rules. I think the way we've actually gone about specifying the sequential elements of it makes it very straightforward. And in fact, if you come to our stand, we're showing a demo where we're automatically generating OpenGL code that generates 3-dimensional graphics and rotates them and stuff. It's literally a dozen or 2 lines of code to define the rules for the orders in which the OpenGL can be called. Okay, so it really is very, very straightforward. I did some work for a customer the other day where he was looking at OpenCV, and we put something together in half a day that was generating stuff and able to test the system.
I'll try and come and have a chat afterwards if we've got time to see how it's done.
I would like to add as well, as I say, we've done this in hardware verification for a long time, and I think these guys are doing a great job in bringing it to software testing world. And in hardware verification, the value is, with virtually the whole industry does this now. So, absolutely. So I think these guys are doing a great job in bringing it to software as well. There is one more question, apparently. Oh, Doc's wants a question. Sorry.
Interesting, and it sounds very similar to the exploratory test automation, right, except for one thing. You haven't mentioned how you know whether a test has failed. Do you generate expected results?
Absolutely. So it's the question. It's probably the most popular question I get asked when I go to talk to this about customers, and it's absolutely vital. So if you're doing any sort of automated test generation, you need to know, did it pass, did it fail, and so on. And generally, what we see, there are at least 3 different techniques that we use for sort of checking. There's the Oracle type concept, or golden reference model, where, for example, with the OpenGL, you might run it on a Windows platform, you might compare it to your Android platform, you run both and you do some comparisons. You might have to apply an algorithm to do the comparisons because they're not necessarily exactly the same, but you do that sort of thing. We also use assertions an awful lot with customers. Actually, within our libraries, we have some assertion capabilities, although there's nothing I guess, amazingly outstanding about assertions. But if you build assertions into the flow, into the methodology, then actually as you make each step, you make each decision in the tree of what I want to do next, you can write an assertion or activate an assertion which says what sort of thing you expect. And that's a powerful methodology for doing checking. And then, of course, there's end-to-end stuff. I sent some data in my wireless network here. I expect it to pop out over there. I can do end-to-end checking. So what we see in reality is most checking environments are a combination of those things. And absolutely, it's a place where you do have to invest time and effort. The engineering effort that goes into building the verification environment, a significant part of that is thinking about the test strategy, the checking strategy, and how that's going to work. So absolutely part of the process.
Thanks.
Okay, thank you very much.